whatever your, the form of the torque. So here is an example of two very simple transformations. So here you have a twofold symmetry, two-fold rotation symmetry. Okay, you have X, Y, Z, and just assume that you basically rotate around. So in this case, you rotate around the Z-axis. It's not very clear, but you take this point and you just rotate it around the Y-axis. Take a point and rotate it by pi around the Y-axis. And well, you can write your rotation matrix. You take your response tensor for the field like torque. So what you say that the field that is induced by the electric field as this tensor form. Okay, and this guy is Ex, Ey, Ez, and you have of course 9 coefficients. So I will not write all of them, but basically you have 1, 1, blah blah blah. You have all your 9 coefficients. You write your rotation matrix, and you perform the transformation I was mentioning. You just impose that this response tensor must be equal to something like that. I'm not sure that the minus is correct. It's before. Yeah, it's fine. So we're not going to do that, but because it's not, again, I mean, for this transformation, it's very easy, but of course, if you take a bound group with 3, 4, 5 different transformations, then well, you have to do it. You have to take all of them, you take your tensor, and you deduce all the coefficients just based on this analysis. So one example here is that if you have this two-fold rotation, you end up with this form of the tensor, which means concretely that your field is such that along the x direction, your field will be something like Ey plus Ez. Let's assume that we are only a two-dimensional system. It would be just a little bit easier. Then I don't have to take care of the Ez coefficient. Then I have nothing. Well, no, I have something along the, if I apply a field along the y direction. And again, I have this coefficient here, Ex. So basically, if I have a two-fold rotation, if I have my gas, I have this two-fold rotation. If I send a current along the x direction, then the Rashba field, if you wish, will be along x and z. Okay. X and z, if I apply a field along x. And if I apply a field along y, what I'm going to have is only a y component. So I can have some very unusual behavior. I just remind you that the Rashba field, if you take this inversion symmetry breaking, should be something like that. Z cross E, or some coefficient minus EY, EX, 0. So this is the form we are expecting if you take inversion symmetry breaking. But if you take other form of symmetries, then, well, of course, you have much more interesting, much richer behavior. Again, if you have this mirror symmetry, you have, you have a mirror, let's say, in the XZ plane. So only Y gets a minus upon the transformation. You have actually the complementary of this matrix, right, with the zeros correspond to the non-zero part here, and the non-zero coefficients here correspond to the zeros here. And in this case, again, what you directly read is that if you send a current along the x direction, so in the symmetry plane, what you have is the field along y. Sorry. So if you send a current along x, you're going to get a field along y. If you send a current along y, you're going to get a field. Yeah, a field along x and z, so in the plane. So keep this one in mind. I'm just going to do it again, because we're going to see a concrete example of that in 1 minute. So now I have this mirror symmetry, and what we just said is that if we calculate the field, we're going to have the x coefficient, along x we have something proportional to ey. Along the y coefficient, y direction, we have something proportional to x. Of course, the coefficients here are different. Yes, and the y, and then we have also some ey here. Okay. So keep that in mind. And what I find particularly interesting is that these kind of unusual symmetries have been observed experimentally. So here I'm giving you an example. I'll not spend too much time on this one. I'm going to spend time more on the other one. So it's a manganese nitrate antimony. You know, you are part of this?
Yeah,
you're a part of
my pictures.
So it's actually, so you recognize the colors. So this is actually most of Yakub's work, by the way. So what is interesting here that the point group tells you that you should have this kind of response, which is, okay, we have to trust me here, which is what we call a Dresselhaus-like behavior. So if you send a current along this direction, the field should be along the current direction. If you're sending along the the y direction, the field should also be aligned on the current. And if you're sending along the 110 direction, then the field should be perpendicular to the direction. Okay, so the field will actually rotate this way, which is, well, which corresponds to the kind of spin momentum locking you have in a Dresselhaus material. So we're going to arsenide with strain, if you wish. Now, what is interesting that experimentally what they got is that, which is actually a combination between this Dresselhaus that is coming from the point group and something else that actually has the Rashba symmetry. And correct me if I'm wrong, but this is actually associated with shear strain. Right? So you basically have, this is coming from strain, this is coming from the crystal structure, and you end up with something like that. So just an example of how things can become interesting. Now the work I want to talk a little bit more about is tungsten ditellurium. So that's an experiment from Dan Ralph's group in Cornell. So you have inversion symmetry breaking, right? You have your tungsten ditellurium, and on top you put your pumballoy. So you have inversion symmetry breaking that gives you the Rashba, the damping, everything. I mean, I would say the lowest order response. What is interesting is that in this particular material, you have this mirror symmetry here. Okay, so it's typically something like that, with the same M symmetry I was mentioning. And what we know from this analysis is that if we have a mirror, let's say here, and if we send a current in the mirror, we're going to have, well, something rather boring. So we're going to have a field this way, okay, along the y direction. So this is Ex, and we end up with an Ey. So that's typically like a Rashba effect. But if we now send it perpendicular to the plane, so to send the current here, what we end up with is a field along X, and most importantly, a field along Y. So those two fields here are not very surprising. They pretty much look like a Rashba field, or is perpendicular to the electric field. But what is interesting, it's easy. What is interesting is this perpendicular part here. Yep.
Sorry, quick question. Because you're talking about field direction and current direction interchangeably. We're talking about charge current right now.
Yeah. So I apply an electric field. So I have a charge current flowing in my system. And this charge current creates a Rashba field, if you wish. An effective field that then will torque the magnetization. So you're right, yeah, indeed. Should be more careful. So this perpendicular field is important because this one can switch the magnetization of perpendicular magnetized systems. So when you have a magnetic bilayer, you don't talk too much about that because I was really focusing here on the symmetry. But let's imagine that you have a ferromagnet with perpendicular anisotropy, and you send a current in the heavy metal. So we send a current here, and we have all sort of torque on this material here, on this magnetization here. So we have this, we have the M cross Z cross E torque, which is our Rashba field, and we have the damping torque. What is interesting is that those torques are non-zero when the magnetization is out of plane. When the magnetization is in plane, so they actually tend to bring this, the magnetization in plane. And once it's in plane, then they go to zero. So you cannot switch those guys. They can actually excite the magnetization. Okay, they can actually bring it in the plane. But if you turn off the current, the magnetization has 50% chance of going down and 50% chance of going up. So there is no switching. To switch, you need to apply another magnetic field, external magnetic field here. And once the magnetization is in plane, this external magnetic field will kick the magnetization down. And then you will be able to have reversible switching. So that's actually an inconvenience in the spin-orbit torque, is that you always need the coexistence of the charge current plus the magnetic field if you want to have reversible switching. And of course, if you want to make a memory out of that, it's pretty bad. Because for memory, you want it to be scalable, so you don't want any external field. Because to generate this external field, you need Ørsted field, you need some wire, it's pretty bad. So what you would like, in principle, is to get rid of this external field, but for that you need a new torque. You need a new component of the torque that will complete the switching. So your damping field like they can break the magnetization in the plane, and then what you would like is to have another torque that actually completes the reversal. What is interesting here is that because of this mirror symmetry here in tungsten and tellurium, this perpendicular field does the job. Because when you are basically in the plane, then this perpendicular field can complete one way or the other, the magnetization reversal. So there have been some experiments very recently where I think this has been achieved. It was probably last year, so I didn't show it here. I just wanted to focus on the symmetry. But this is to tell you that the crystal symmetry of the system that you are working with can be very useful and can be engineered to complete the magnetization and to have some field-free switching. So, of course, if your name is Jakub Zielejny, then you do it for all the possible bond groups. So if you have a favorite bond group, please contact Jakub and we'll calculate the torque. So he has done it for all the 32 bond groups, and this is actually exactly the topic of his presentations, among other things. So I will not talk too much about that. But you get that by doing this symmetry analysis and by performing the symmetrization of your response tensor for the field-like torque, the damping-like torque, and actually pretty much anything you want. The last thing I want to mention, and that's kind of an introduction to the last part of this lecture, so within 2 days, is an experiment that was done by Chen in NUS. So Chen is an expert in growing perpendicular materials. He has been working with industry to grow perpendicularly magnetized materials for data storage. And a couple of years ago, 3-4 years ago, 3 years ago, he actually came with this copper platinum L11 material. So this is the image where you have this copper platinum, cobalt platinum, and the good thing is that there is a very small lattice mismatch between those two materials, and most importantly, they grow in the L11 direction. So here you have this unit cell. You see, you have this threefold symmetry plus a mirror here. Okay, so this is a C3V material. The point group is C3V. So threefold rotation plus a mirror symmetry that in the plane that contains the axis of rotation. So what is interesting in this particular material, of course, you have this the threefold symmetry, so you would expect something to happen in the 1-1-1 plane. And indeed, what they got is that he measured the current-driven switching. So he has this cross where you have your cobalt platinum. It's cobalt platinum, so because of the strong spin-orbital coupling, the magnetization is perpendicular. So you send the current through the cross, and what it actually gets is that without external field, depending on the direction, on the relative direction between the current and the crystallographic axis, it can get field-free switching. So it brings the magnetization in plane, and something happens that completes the reversal. So if you send the current along the low symmetry direction, okay, here you see there is the mirror symmetry is here, so you actually are perpendicular to the mirror. In this case, you have this very nice hysteresis loop. Then if you send the current along the high symmetry direction here, the mirror, the inside the mirror plane, there is no field-free switching. You can switch with the field, but without field, there is no switching. And quite funnily, if you send it along this direction here, now you have the switching, but with opposite polarity, and so on and so forth. So you have +0, +0, and so on. So of course, there is something that this C3V point group is bringing to the physics here, and this is something that we will look at more carefully, probably next lecture or the last one. We'll see. Hopefully next lecture. So I'm done for the spin-orbit talk part. You guys have any questions on that? Yeah.
So for this, so for normal SOT, you need to stop sending the current in order for.
Yeah, you actually send a
spin
pulse.
Redux.
You send a pulse, right?
Yeah, but I mean, with spin redux back, or I mean,
so normally, if you just have damping and feed-like, so you don't have these 3 and 12 that we propose here, the magnetization has, let's say, 50% to go, 50% chances to go back up or down. And of course, you have domain walls. I mean, you have domains, which I don't discuss here.
While sending, I mean, if you keep sending current, damping like torque.
If you keep sending current, the torque is 0 when the magnetization is in plane. So normally the magnetization should stay in plane.
In plane, yes.
Yeah.
But for this field-free one, what happens? It's just immediately go to the final state.
In this particular case, yes.
And this was a very, so this, I mean, if you keep sending a current, you mentioned that spin has to be this in plane. Has been confirmed experimentally by any?
No, because it's actually a transient state. So
it's too hypothetical.
Yeah,
it's a hard
I mean, if you do if you do a macro spin model, then of course it works.
Yes, yeah.
It's macro spin, so it works.
Yes, it works. Yes. But experimentally,
yeah.
Does anybody see this?
I don't know, but it's a hard axis, right? So I mean, it cannot stay there, right?
No, well, I mean, if you keep applying the torque, then basically
What torque? You said torque vanishes.
Yeah, but then when you get out of plane, the torque is not 0 anymore. So
oh, okay, so it would kind of be.
Yeah. It would basically. That's why it's a transient. It's definitely not stable.
Yes. Question. So just wonder how good the C3VE symmetry is. I imagine if you rotate the structure by 180 degrees, it may still exist, but with a 1 atomic layer displacement.
Ah.
Right. So are there structural domains? And do they know?
Ah, that's okay. That's a good point. I haven't thought about that. Let's see. So what you see that the planes here are rotated by 180 degree, not 90, right?
Yeah, 180 or.
But you're right. I mean, if there is any roughness, then you could expect. Interesting. Okay, I have to look into the angular dependence of the torque. I will think about that, because indeed the thing that the torque that destabilizes the magnetization is the damping line. So you don't need to have a very clean interface, as I said previously. If you have some, I mean, this threefold symmetry, this T3V symmetry doesn't have impact on the damping torque. The damping torque just needs invariant symmetry braking. So the destabilization is very robust. Now the question is the other torque, the 3M torque, the torque coming from the C3D symmetry, and that is completing the reversal. This one has an angular, I have to check that, but I would tend to think that the 180-degree rotation does not impact the sign of the torque. The 90-degree rotation would. So if you start having some crystals, then you might indeed have some conservation.
Okay.
But that's I'm not entirely sure. I have to check that. Yeah.
So in the next slide, like if you see this pattern of spin, like it's rotated by like 60 degree, right? The 30 degree state,
Yes.
and it's 90 degree. So it's like C3 rotation or the C6 is important for this one. So like the spin pattern is just like similar when you rotate by 60 degree, right? Because at 30 you find 0, then again 90. The next one term it's 150.
Well, I mean the polarity is different, right? The sign is different.
And sign is related to the meter, right?
So basically it's so the correspondence is between 0 and 120 degree. 60 as the opposite polarity,
Okay.
which means that in one case the additional torque complete the reversal down, and the other case you actually complete it up, right? So if you start up, in one case you will switch. So let's say you're going to switch here, but not here. Okay, you will basically go from the down state to up, and here you're going to stay at the down state. Okay. But if you actually start the other way, you start this way, then you stay, and here you switch.
Okay, thanks.
So now I'd like to say a few words about the Jozinski-Murray interaction. So we have seen the torque. Now let's talk about the Jozinski-Murray interaction. So, and this slide is rather for the theorists in the room, just to kind of understand where this D dot S cross SI cross SJ is coming from. So I will assume a very general form of the magnetic energy. And I will say that this is it's bilinear. I mean, it's just an SI dot some matrix or some tensor dot SJ. And so that's a very, very general form of my energy, and I can separate it into different terms. This term here is the symmetric part of this tensor. This guy here is the anti-symmetric part of the tensor. Okay, you can say that you can always write your tensor, whatever it is, ij, as ij plus ji plus 1/2 of ij minus ji. Okay, it's a very, very, very simple symmetrization. This guy will actually give you your Heisenberg exchange. Will actually force the spins to be parallel or anti-parallel with each other. And this guy, if you look at you can actually develop it, so we're not going to do it here. It's not that difficult. So it's a 3x3 matrix at the end of the day. You can show that this guy will actually give you an anti-symmetric exchange, which must be of this form. There's no other way, at the second order in spin, okay, you have two spins here, there's no other way you can write the exchange. It's always this term plus this term. The same thing as if I symmetrize my exchange. And of course I have some anisotropy, but this one I don't really care. Okay. So I can also look into my energy not on the atomistic level, but on the continuous picture, the macromagnetic picture, which means that I need to do that. I basically assume that my spin is essentially the local magnetization plus some deviation. Okay, and if I some deviation along some direction, so of course you have some, you need some gradient here, and if you do this kind of expansion, you end up with again a term that is quadratic in gradient, a term that is linear in gradient, some anisotropy, and so on and so forth. The reason I want to show that is because the spirit is very different, and depending on the picture you take, whether you take the atomistic picture or the continuous or the macromagnetic picture, you are not going to calculate Jaworzynski-Moravia in the same way. And if you look at the literature, there are 4, 5 different ways to calculate the Jaworzynski-Moravia interaction. They kind of give you the same order of magnitude, which kind of makes sense, in fact. But they have their own limitation. So there have been a lot of, well, actually, surprisingly, there have not been many debate on that, although there are many ways to calculate it. And I think the reason why there are not many debates is because that's a tricky, the calculation it's rather tricky. So here you see when I'm expanding my macromagnetic energy in the gradient of the magnetic field, the magnetization field, it's actually pretty similar in spirit to what Oleg showed yesterday. Of course, I have a quadratic term that is usually associated with the exchange, but I have a linear terms that is not directly the Jaworzynski-Moravia interaction. Because the linear term, again, you can symmetrize it. And if you symmetrize it, you will have a part that is symmetric and a part that is anti-symmetric. The anti-symmetric part is the Jaworzynski-Moravia interaction. But you could also have terms like that. I'm not going to talk about that today, but this term, you see it as an interesting structure. You have I, J, K, K, J, I. This is called, does anybody know what this is called? A Lifshitz invariant. Have you heard about that? I don't know why is it invariant, by the way. So if somebody can answer.
Lensor theory.
Yeah, I know, but invariant on what?
Under symmetries of the system.
On the symmetry, but this is a rotational symmetry, right, or something like that?
No, whatever symmetry the system has, these have to be invariant under that.
So that's actually a question I have. So the antisymmetric part is actually to this particular form, which basically stabilizes fermions and chiral structures. So basically it bears some chirality. The symmetric part does not.
Well, the symmetric part, if you integrate it, it boils down to surface terms, and that's why it's not important.
If you don't care about surfaces, right? So that's it. So in this case, this one, okay, I see what you mean. Okay, so this one basically fulfills the symmetry of the bulk of the bulk system, and this one does not need because it's actually an interface. Okay, no, I get it. Okay, makes sense. Because this one, in fact, creates some canting. Okay, so if you take your if you take a material with some sort of with this term here that is linear in the gradient, the anti-symmetric part of your linear term, so the one that is proportional to this Lifshitz invariance, will give you chirality, so it can stabilize spin spiral, it can chiral spin spiral, can stabilize fermions, these kind of things, even merons, so some interesting systems. But the symmetric parts will actually act at the edges, and will actually count the magnetization at the edges. So it doesn't create a chiral texture per se, but it creates some counting. So it could actually have some interesting behavior right at the interface that is different from the bulk. Okay? So the Jaworzynski-Moravia interaction is not that. It's that. This is the Jaworzynski-Moravia interaction. So now you have two expressions of the anti-symmetric exchange in two limits, in the atomistic limits or in the macromagnetic limit. And of course, whether you assume one or the other, it's not exactly the same. It doesn't give you, exactly the same physics. Of course, this term here with the Lifshitz invariant is valid for smooth gradient. It's a gradient expansion. So it means that the gradient must be smooth, must be very small, in principle. So if you have any nanoskirmion or any very strong counting of the magnetization, this one is not valid. You have to go way beyond the linear approximation. Okay? But on the other hand, if you have very smooth gradient, you know, this one is ij, so basically it's between site I and site j. So if you take a very smooth gradient, in principle, let's take this a chain like that. In principle, you should be able to take into account the Johansson-Skimmer interaction between nearest neighbors, also between next nearest neighbors, next nearest neighbors, and so on and so forth. And I'm going to say a few words about that because I think it's not. One has to be careful. Okay. Well, from the I will probably go fast on this one. From the symmetry point of view, if you want to look at this kind of system, you take two magnetic moments embedded in a lattice. So it could be in a gelium, it could be in this kind of system. The exchange can be computed using Green's function using this kind of formula, you know, the trace of the exchange between the itinerant electrons and the local spin, itinerant electron and the second local spin, and then some propagator here, which is essentially a Green's function. And it's kind of technical, but your Green's function can be approximated as the one without spin-orbit coupling plus the one with the spin-orbit coupling here. Okay, that's for the few theories in the room. When you implement this Green's function inside this trace, you see that in the absence of spin-orbit coupling, this guy is diagonal in spin, so it doesn't act on those operators here, and you end up with a trace of sigma dot SA, sigma dot SB, and this trace gives you SA.SB. So that's your exchange. That's one way to compute the exchange between neighboring magnetic moments. Now, if you look at the first order in spin-orbit coupling, so the spin-orbit coupling will be sigma dot some effective field. This is what we saw in the previous lecture. In this case, you have this trace to take into account. So sigma dot SA, sigma dot B, sigma dot B, SB. And we take the trace. What you get is this nice cross product, okay, which is nothing but the Johansson-Skimmer interaction that I showed you previously. Okay, this is just to give you some microscopic feeling where this is coming from. Okay. So there have been many. I'm not going to talk about the very mechanism. There have been many mechanisms that have been proposed. It was first studied by Moria and Jawosinski in the case of weak ferromagnets. So Moria has a theory about super-exchange. Albert Fert has a theory about RKKY. There are different scenarios that are proposed. I would say no that we have density functional theory. I'm not completely convinced this is. I mean, of course, in dilute system, this is a different story because the DFT is difficult. But if you look at transition metals or at bulk materials, well, I'm not sure any of this distinction is meaningful.
So
yeah.
You may question, is the reason this formula looks very much like a Landauer formula?
Yep. Yeah, it's a response function. Yeah. It's a response theory. It's a good idea. Yeah, it's a good point. So Moria actually, so a few years after Jawosinski came with this exchange, Moria came with a number of rules, of symmetry rules about this vector D. So remember that those rules apply to this atomistic Jawosinski-Moria interaction. Okay. So the idea is that I take two magnetic moments, and I look at the symmetry, at the crystal symmetry, or the symmetry of the crystal field around this line between I and J, and depending on the properties of this environment here, I will have different behavior of the Jawosinski-Moria interaction. So if there is an inversion symmetry between, let's say, site A and site B, then I should not have any Jawosinski-Moria interaction. If I have a mirror symmetry, then the Jawosinski-Moria vector should be inside this mirror. Okay? If the mirror symmetry is perpendicular to the AB axis. Now, if the AB sites are contained in a mirror plane, then the geodesic scheme area must be perpendicular to the mirror plane, and so on and so forth. I'm just not going to describe everything. You can have a look at the Moria paper. But basically, just by looking at those 5 rules, you can determine what is the direction of the vector. And this is something you can do very easily. If you take a Kagome lattice, for example, yeah, that's probably a good way to visualize. If you take a Kagome lattice, so Kagome is something like that. Oh, yeah, okay, kind of. Let's say I'm going to put some magnetic moments here. And you immediately see that there must be some Josin-Scheme-Area interaction between this magnetic moment and this magnetic moment. The question is, so I'm looking at this line, AB. So where do you think the Josin-Scheme-Area interaction is pointing? So here I have a vector, so I have SA, SB. And the Josin-Scheme-Area interaction should be SA cross SB. So if you look at Moria's rule, where should the Josin-Scheme-Area interaction point to? So we can look at this guy. Okay. I have a mirror plane here. So Josin-Scheme-Area Moria, sorry, not Josin-Scheme. Moria tells you that the DMI should be perpendicular. So in this particular case, what I have is a D Z dot SA cross SB. Right? And you know that very well. So this is a very simple rule of thumb, and then you can deduce what is the vector direction in many configurations. Of course, it doesn't tell you the magnitude, but it can help if you have to do some DFT calculation. Now, I would like. So, do you guys have any questions on that? Because what I would like to do now is to mention, just for the sake of the discussion and for your information, the ways Josin-Scheme-Area interaction has been computed from density functional theory. And I think it's very important to understand the advantages and limitations of the different techniques. I'm just going to show 3 of them. I'm not going to show the the KKR technique. Well, I can just, okay, well, very, very, very quickly. There is a density functional theory technique that calculates directly the exchange tensor. And if we have the exchange tensor, you can deduce to Josin-Scheme-Area. You know, this is this big lambda ij tensor. Okay, if you get this tensor from density functional theory, then you can deduce Josin-Scheme-Area interaction. But this is, of course, assuming the atomistic point of view. So the first. It's not the first, actually. It's, I would say, one of the most influential calculations of Josin-Scheme-Area in transition metals was due to Ho-Ching Yang and Malbec Chief. And so they were actually working on platinum-cobalt interfaces. Yeah, you have your cobalt here, and you have a bunch of platinum. I don't show all the layers. And what they did is that they actually created a spin spiral in real space. So they take a supercell and they impose the magnetic moment direction to rotate either clockwise or counterclockwise. Then they calculate this energy, they make a difference, and well, they don't have the Josin-Scheme-Area yet because they have some energy difference between the 2 chiralities. And then, well, you have to be smart and consider that when you create a spiral here, you also create the same spiral here and here, right? You know, it's a supercell. So this cell is the same as this one, the same as this one, and so on and so forth. So if you create a spin spiral here, of course it's infinite in this direction, but it will also be repeated here and here. So the energy, the magnetic energy that you are calculating, is coming from, at least in the atomistic limit, when you assume, when you look at the Heisenberg plus Joseph schema exchange, you have to, the energy you get is coming from the interaction of this guy between this guy, this one, this one, this one, this one, and so on and so forth. So you have many nearest neighbors. So in principle, what you should do is, I mean, you basically have to compute, I mean, to determine, so assuming a form of the Joyce schema area, you have to determine its contribution, its hypothetical contribution to the total energy of the system. And then you can deduce a coefficient. But you see the problem is that, so that's a rather fast method to calculate the Joyce schema area interaction. You have to make no assumptions on the spin-orbit coupling or the exchange. So normally it works for, it's a very, very easy to use method. But there are, in my view, several issues which are not secondary issues. The first problem is that when you do the calculation, what you get, it actually depends on the interpretation of the calculation you get, will depend on the number of nearest neighbors that you will assume in your model. So what I mean is that you have a calculation that gives you a number, okay? I don't know, let's say 1 millielectron volt. That's your number. Now you have to interpret this number in terms of this model. So you develop some analytics, you get some formulas, and you will have something, I'm going to say something stupid, I don't know, you're going to find that the square root of 3/2d is equal to that, then you can deduce d, okay? But if you do this kind of thing, then you are assuming that the Joyce schema interaction is only nearest neighbor. But it's a metal, okay? It's a metal, so in principle, you don't only have nearest neighbors. You have nearest neighbor, you have next nearest neighbor, next nearest neighbors, and so on and so forth. So that's the first issue, is that normally your model should be much, much more complicated. With, of course, the nearest neighbor here, you should have the next nearest neighbor, the next nearest neighbor, and so on and so forth. And of course, you're going to have a lot of unknown. I mean, the more accurate you want to be, the more d you're going to have to determine. But you only have one calculation because you only set one spin spiral. So the only solution you have if you want to be accurate is to increase the unit cell and create smoother spin spiral. And that becomes very, very computationally demanding. So that's the first issue. So that's inadaptive to metals in my view. It's fine for insulators though, because in insulators it's mostly nearest neighbors. Well, this can be argued, but anyway. There is a problem with the penalty cost imposed by the fourth theorem, but I'm not going to talk about that. The problem also is that it's impractical for long wavelength. So if you want to model the Joyce schema area for a skyrmion is typically 20 to 50 nanometers wide. Okay, if you go for nanoskyrmion, it's going to be 2 nanometers. But 2 nanometers is already several of the lattice parameters. So it's much longer than this spin spiral. This spin spiral is extremely, extremely short. So basically, this is fine for extremely short spin spiral, but not for long spin spiral. And so that's I think something that we should be very careful, especially that in this paper they claim that the Joyce schema area they obtain is similar to the one people observe in experiments. I would say, fortunately, it's similar, but doesn't mean this is the right one. Okay? Yeah.
So is this method work for all kinds of structures?
Yeah. I'm not. The problem is that this is not accurate. Okay. This is the big issue. This is for metals. It is not accurate. So you have to be more careful. So another method that was developed by actually several people that I've been working especially with the Blugers group is the general block theorem. So you know the block theorem. You already heard about it. Now, if you take a material with magnetization but without spin-orbit coupling, and you imagine that you create a spiral, a magnetic spiral. What you can demonstrate, because there is no spin-orbit coupling, the magnetic spiral is simply a rotation of the quantization axis. So when you compute the wave function of this system, you don't need to bring new information. All the information is already contained. Sorry, there is an up here. That's a mistake. It's already contained in the block wave function of your homogeneous state. So you can calculate the block functions for the homogeneous state, create a spiral, and deduce the wave function of your spiral state. Okay? Very, very beautiful. Again, this is up spin. Huh? Once you have this wave function, the idea is to take the spin-orbit Hamiltonian and to project this spin-orbit Hamiltonian on this spin spiral wave function. When you do that, as a function of the wavelength of your wave function, you get a dispersion that kind of looks like the one you have for magnons. Huh? It's kind of quadratic dispersion. And so when there is no spin-orbit coupling, the dispersion is symmetric in K, and when you have spin-orbit coupling, you can have some very dramatic change of shape, and the slope here will give you Jasinski-Moriya interaction for the long wavelength. So it's very well adapted for the long wavelength case. The main limitation is that you can only calculate the effect of the spin-orbit coupling on the from a perturbation theory point of view. So only to the first order, perhaps second order in spin-orbit coupling, but things can become very, very quickly difficult. So it has been massively used for transition metals interfaces. There are a number of very impressive papers that are collaboration between the Blugers group and the Wiesendanger group. That's one of them, where they can actually observe experimentally some spin spirals in their structure and compute the Jasinski-Moriya interaction using this method. So I'm a big fan of this method, I have to be frank. But of course, you have this limitation that the spin-orbit coupling cannot be too strong. And the question is, what does too strong mean? Kind of unclear. The last method I'd like to mention is in my view, kind of interesting. So the idea now is to take the gradient expansion. So you compute your magnetic energy using a Keldysh formalism, for example, and you expand it to the gradient of the magnetization. So you're going to have exactly a Green's function formula that gives you the Jasinski-Moriya interaction. So the big advantage is that you don't make any assumption on the spin-orbit coupling. And this is adapted to long wavelength by definition. So if you want to compute Jasinski-Moriya for skyrmions, that's the way to go, in my view. Well, the problem is that it's only for a small gradient, smooth gradients, so long wavelength. So if you start having some small effect and you need higher orders, well, then you have to develop these kind of formulas for second to third order expansion in gradients, and that's absolutely horrible. So this is the Wigner expansion. It works very well if you look at first and maybe second order expansion, and even second order you have like pages of formulas, but third order it's impossible. So anyway, yes, all have their limitations. I will, I will just probably stop here. Just show you an example of the kind of thing that the Jasinski-Moriya interaction can do. So if you take iron copper, sorry, is there any question? Don't stop. Okay. So if you have, let's say, this iron cobalt silicon material, it's a B20 crystal, so it's cubic but has inversion symmetry breaking. You can show that your Jasinski-Moriya interaction has this form in the continuous limit. And what if you do some Lorentz-TM imaging of the material, so you have to apply magnetic field at low temperature, what you start seeing is that at low magnetic field you have some nice spirals. Okay, you have a rotation here, it's going this way. If you increase the magnetic field, you start having some interesting pattern. Okay, this is and the emergence of your Schumann crystal. And of course, if you heat the sample, it's actually as a function of the temperature. So you increase the temperature, you go from space spiral to disordered Schumann state to nice crystal, Schumann crystal, and then to nothing because you heat the system and then there is no magnetation anymore. And as I was mentioning previously, it has also been observed at room temperature in magnetic multilayer. So in this case, this is nickel-iron copper interface. When now you don't have a Schumann crystal, you actually have a metastable Schumanns, but you still have some nice chiralities. What I want to attract your attention on is the form of the Josephson scheme array. So this one looks pretty much similar to the damping torque we talked about, or to the field-like torque. You know, in the damping torque or field-like torque, we have this M cross Z cross electric field cross M, and that's because of the inversion symmetry breaking at the interface. If now you look at the Josephson scheme array interaction, you're going to have M dot, because it's an energy, Z cross the gradient cross M. And actually those guys are very similar, because E and the gradient, they are both polar vector. Interesting. Now if you go for the B20, B20 has inversion symmetry breaking in the ball. It has this cubic structure. So what you have is not a Z cross gradient, because there is no preferred direction. It's a cube. So X, Y, and Z are equivalent. And in this case, what you have is a gradient directly. It's not Z cross gradient, it's just directly a gradient. And of course, if you go for even crazier kind of Josephson scheme array interaction, you can stabilize, I don't know, untest Schermions, Meron, anti-Merons, all this stuff. Okay, there's a lot of excitement, a lot of work on that at the moment. So that concludes the part of the Schermions on the Josephson scheme array interaction, in fact. So is there any, yeah?
Thank you. I have a question. You show 3 different methods to theoretically compute the DMI. There are some experimental methods to measure and contrast the DFT.
So I would say if you want to compare, probably, okay, the difficulty I think is that when you do DFT, your system is super clean, and in experiments, in the mainstream experiments, especially the magnetic layers, your system is terrible. There's a lot of roughness and stuff like that. So I think comparing quantitatively, you're going to have an order of magnitude that would be actually all these methods give you the same order of magnitude, which kind of makes sense when you think about it, because you basically have exchange, spin-orbit coupling, inversion symmetry breaking at the interface. So if the potential drop at the interface has the right order of magnitude, if the orbital overlaps is kind of the same in the different methods, then you should have the same number. Magnitude. However, it's very hard to, I don't think the experimental methods are accurate enough to distinguish between the different approach. One way to do it would be to either look at pathological systems, iron iridium. Iron iridium is terrible because it basically you have reconstruction in the interface. The magnetic moment of iron is diluted into the iridium. So iron iridium is a very pathological system for this kind of physics. So probably if you take this pathological system, you might be able to distinguish between the different theoretical methods. Another thing would be, and that's kind of connected, to work on these kind of systems. So basically the STM experiments from Wiesenberger group, typically, when you have a very clean surface with very clean chains of atoms. So the system is a model system, and then you can benchmark your calculation, because it's what you see this calculation here, right? So the line here is the theory, and the points are the experiments.
Yeah.
It's like, wow.
Yes, very good.
So, Yeah. You mentioned on this slide that this calculation is pretty heavy. What's the region of the
I have
calculation?
no idea because I never do the calculations. Okay, I don't do DFT. I have a fantastic postdoc that does DFT, fantastic collaborators that do DFT, but I don't do it. But it's, I mean, I remember that for the work that we did with that, it was, we had like terabytes of information to deal with, to dig into at the end of the day. But I mean, we were working like 30 different systems, so. Yeah.
Could you elaborate in the first method exactly how you get from the difference in energy of the two opposite chiralities to the Legensky vector?
Okay, so I will not do the math, but I can. Okay, so you create your two, let's say your clockwise and counterclockwise spirals, and then you calculate your energies. Okay, so you end up with. So that's what you get from numerics. Okay, you do your DFT calculation, you get that. Now what you need. So let's say you have your. I'm just showing the magnetic atoms. So your unit cell is here. And now what you need to do is to say, okay, I have other atoms here. I'm going to model my magnetic energy. So the energy of my spiral will be the exchange between this guy and his nearest neighbors. So we'll have the exchange between this guy and this one and this one, this one, this one, this one, this one, this one, this one. Okay. So you have to sum. That's, let's say, I. This is I. With all the SJs. And of course, this one is, let's say, up. This one is here. This one is here. This one is, yeah, here. Okay. And you have the same here. So now you have to, so that's just the exchange. So you have to compute, to say, if J is a constant, because it's nearest neighbors, right? The distances are all the same. So you would have this one scatter this one, which is 0. This one scatter this one that is non-zero. This one scatter this one that is 0, and so on and so forth. So you have to do all your, bookkeeping, essentially. And then you have the Josephson-Skimmer interaction. You say, okay, now I have Josephson-Skimmer interaction between this one and this one. It's perpendicular, so it's non-zero. Right, so you have a Josephson-Skimmer interaction here. No Josephson-Skimmer interaction here. A Josephson-Skimmer interaction here. Let me think, but that's here. That's let's see. I'm lost. Anyway, you understand, right? So then you actually end up with a big it's a small coefficient with a coefficient that will take into account all these interactions, and then you have to do it again for this one, and then for this one, and then for this one. So of course you have a lot of symmetries in the system, but that's only for the nearest neighbors. But normally you also should have next nearest neighbors. So now you have a second term. So this is D1, this is D2, and you have to do it again. So you have, well, it's kind of a lengthy, boring calculation, but it's rather straightforward.
No, so when you take a difference and your symmetric exchange drops out.
Yeah, absolutely, yeah. So then you say I have this chirality, then I have the other one. So the other chirality should basically change the sign here, but not here, and make a difference, and you can have twice the energy. Okay, I will just probably, if I take one more minute, to make a connection to tomorrow's lecture. Okay, so what I've been doing in the past 2 hours was to talk about the microscopics and kind of the microscopic physics behind spin-orbit torque and Josephson-Skimmer interaction, as well as the general form you can deduce from some symmetry consideration. But the problem that if you want to go further, if you want to go to higher orders in magnetization, even higher order in the electric field, let's look at the second order Hall effect, third order Hall effect, and so on and so forth. Well then, either you apply your symmetry operations on your tensor, but the tensor becomes larger and larger and larger. Or you try to find a shortcut. And tomorrow's lecture will be about this shortcut. The idea is to use the character table of your point group. So it's actually provided by in the literature. So what we're going to do next time that we're going to learn how to build a character table and how to build what we call invariant functions. So if you take us, I think this one is a C3V, I believe. Yeah, it's a C3V character table. So you have different transformations, different representation, and you have. It's actually very similar to what Satoru was talking about. I mean, and actually, I think you also talked about something like that. So you see, you have a lot of concepts that are redundant in this tool, which I think is very useful, very, very useful. We just have different standpoint on those different concepts. So basically, what we're going to do, that we're going to manipulate and we're going to combine those different invariant functions to get the response we want. So either an actual vector or a polar vector or an energy, which would be a scatter, for example. So if we want to get an energy, we know that the energy is a scatter, so it should be in this representation. So we need to combine all these different invariants in such a way that they belong to this representation. Okay? If you want to get an actual vector, a field, so the z component of the actual vector is, oh, it's actually right here. So it's this is an actual vector, so then it should be in the T1 configuration. So you're going to combine all the different invariants to get something that falls in the T1 configuration, and that will give you your field. And that accounts for field-like torque and damping-like torque and any other kind of torque you want. Okay? You can do the same for currents. In this case, you look at the polar vector, and so on and so forth. So we stop for today because I have exceeded my time. Thank you very much.